Hello everybody, this is John Whitaker for the graduate level probability class, and this is our 19th video lecture. And today we want to continue talking about conditional probabilities, in particular with conditional expected values. Last time we ended with looking at the conditional expectation with discrete random variables. I want to start today by looking at conditional expectations with continuous random variables, and that will be our first definition and example. So as a definition, we let x and y be two continuous random variables. Then the expected value of x given y, conditional expectation, is denoted by expected value of x given y equal to y, and defined by the expected value of x given y equal to y. It's an interval over all real numbers of x times the conditional probability density function of x given y. And you integrate with respect to x. So that's its definition. Excuse me. Let's do an example. Oops. So as an example, let's let x and y be continuous random variables. With joint probability density function. Okay, so here's what it is. It's f of x comma y equal to, so something we've looked at before. It's 12x if 0 is less than y is less than 2x is less than 1, and 0 otherwise. And here's what we're going to find. We're directed to find the conditional expectation of x given y equal to little y. Okay. So we had already worked with this problem before, and I'm just going to recall from previous work. So from previous work, the conditional probability density function of x given y, what it's equal to is this piecewise defined function. Excuse me. It was 8x over 1 minus y squared if 0 is less than y is less than 2x is less than 1, and it is 0 otherwise. Okay, so using that, we can compute the conditional expectation of x given y. So for 0 less than or equal to y less than 1, the expected value of x given y, okay, it's equal to the interval from minus infinity to infinity of f of x given y, well, it's an x here, dx. Okay, because of the way that the conditional probability density mass, density function, is defined, a lot of times it's 0. So the spot where it's not 0, okay, so I look back at it, the y's are less than the x's, so it's this region, okay? And so what we end up integrating for any one of these y values, our interval comes from this was y equal to 2x. So we're integrating with respect to x. It's 12x times x. And what are we integrating? We're integrating up to 1/2. What are we integrating? We're integrating x equal to y over 2. So that's equal to, so the integral from y over 2 to 1/2, 12x squared dx. That's equal to 12x cubed over 3, so it's 4x cubed, evaluated from y over 2 to 1/2. So taking the 1/2, I made a mistake. All of this, of course, is not good. It isn't 12x squared that I'm integrating. It's the, here, oh gosh. Well, my limits, I think, are correct. But I should be integrating 8x over 1 minus y squared. Okay? And then dx. And so please make that change. So this is the integral y over 2 to 1/2 of 8x squared over 1 minus y squared dx. We can pull out the 8 over 1 minus y squared. And what we're left with is x cubed, when we integrate, over 3, to be evaluated from y over 2 to 1/2. This ends up being 8 over 1 minus y squared times, when I stick in 1/2, I just get 1/8. And if you want, you can pull the 3 with this. So I will. So it's 1/8 minus, here this is, when I stick in y over 2, I get y cubed over 8. The 8's, of course, will cancel. And so what we're left with is 1 minus y cubed over 3 times 1 minus y squared. Now that can be simplified, but I'm not going to simplify it. I'm just going to say that's our answer. Sorry about that momentary mistake. Okay, so that was an example of a conditional expectation for continuous random variables. I want to, well, before I leave, as you look at this example for a second longer, notice that our answer for the expected value of x given y has an expression that's in terms of y. And so did our previous example when we had discrete random variables. And that is indicative of a fact that I'm about to list. So as a fact, the conditional expected value of x given y equal to y is a random variable that is a function of the given random variable, that is y. That's what we have. I'm not going to go into any details about that. The the previous two examples we did are illustrations of that. But that's a fact. Here's a definition. We're going to let X and Y be random variables. We're going to let G be a function of the random variable X. Then, the expected value of G of X given Y is denoted by expected value of G of X given Y equal to Y, and given by, defined by, okay, we're going to have two forms that's defined by, depending on if all the random variables involved are continuous or discrete. So it's defined by the expected value of G of X given Y. So this conditional expectation of G of X given Y equal to Y. Okay. So it's the sum over all X values of G of X times F of X given Y. Or it's the interval from minus infinity to infinity of G of X F sub X given Y dx. Okay, that's its definition. Let's do an example. We'll do an example when we have continuous. Oh, and I should write that too. This is where X and Y are discrete. And this is where X and Y are continuous. So as an example, let's let the joint PDF of X and Y be, so here it is, f of X comma Y, and it's going to be equal to 1/2 Y e to the minus X times Y if 0 is less than X is less than infinity, and then 0 is less than Y is less than 2. And here we're going to have 0 otherwise. And so the directions are going to say, find the conditional expected value of e to the x over 2 given y equals to 1. Okay, so this is the conditional expected value of a function of x, this is like my g of x, given y equal to a particular y value this time. And so here, note the conditional expectation of e to the x over 2 given y equal to 1. What that's going to be equal to is an interval from minus infinity to infinity of e to the x over 2 the conditional probability density function of x given y equals 1, dx. Okay? So I need to find certain things here. So what's the conditional probability density function of x given y? Given 1. Well, that's defined to be f of x1 over f sub y of 1, which is equal to, so if I look over here, that's 1/2, y is 1, so it's 1 times e to the minus x times 1 over f sub y of 1. So, what is the PDF of y? That's the bottom. Let's see if we can figure that out. So f sub y, just y in general, what that is equal to is the interval from minus infinity to infinity of the joint PDF with respect to x. Now, this joint PDF a lot of times is 0. So, so for a fixed y, y's got to be between 0 and 2. What do the x values run from? Well, they run from 0 to infinity. And so what am I integrating? I'm integrating 1/2 y e to the minus x y, and that is with respect to x. So we need to do that integral. Okay, so that's equal to 1/2, I pull that out of the integral. Let me just write it here. So 0 to infinity, it's e to the minus xy, and then it had a y, dx. Now look, you've got e to something. To be able to integrate e to something, you need to derive something. That's minus y. So I need to put a minus here, so I'll put a minus out front of the constant. And now that's equal to, so this is supposed to be an improper integral, but I'm being a little bit informal. This will be minus 1/2. It will be e to the minus xy evaluated as x runs from 0 to infinity. When you stick in infinity for x, provided that y is positive, and it is because y has to run between 0 and 2, that what you get is 0. And it'd be minus a minus 1/2. And here, this one, when I stick in 0, when I stick in 0 for x, this is going to be 0. E to the 0 is just 1, so we get minus a minus 1/2, which is just 1/2. So, what we get is f of x given y. Well, that's what I have. Give me a second to make sure I haven't made a mistake. So f of x given y, of x given 1, that is 1/2 e to the minus x, that's what we had before, all over 1/2, so I just get e to the minus x, that's correct. So now I want to integrate that. So I'm integrating that, so the expected value of e to the x over 2, given y equal to 1, that was the integral from minus infinity to infinity of e to the x over 2 f sub xy x1 dx. And remember, I didn't say this very well, but this is defined, and so the y values run from, well, the y values equal 1, but the x values here will run from 0 to infinity because of our definition of the joint. So 0 to infinity, e to the x over 2, and here this is e to the minus x, and we're going to respect x. Now, that's equal to, so let's see, you could rewrite this as n equal from 0 to infinity of e, so we add exponents to the minus x over 2 dx. So I need a minus 1/2 here to be able to integrate. So 0 to infinity, e to the minus x over 2 minus 1/2 dx. And I have to put a minus 2 out front to compensate for this multiplication, minus 1/2. And so that ends up being minus 2 e to the minus x over 2. So formally, I write down 0 to infinity. When you stick in infinity, this guy goes to 0. So 0 minus a minus 2. When I stick at 0, I just get 1. So we end up getting 2. So our conclusion is that the conditional expected values of e to the x over 2 given y equal to 1 is equal to 2. That's what we have. So we're done with that example. Here's another example, although it's very abstract. It says let x and y be independent Poisson random variables with parameters lambda sub 1 and lambda sub 2. And what we want to do is calculate the expected value of x given x plus y equals to some number n. That's what we want to do. Okay. So we're talking about discrete random variables, Poisson random variables. And so we start off by realizing that the expected value of x given x plus y equals to n. Well, that would be equal to the sum over all x values. So here the x value for Poisson is from 0 to infinity. And then it would be f of x given x plus y of x given n. Okay, that's what we have. So that was from the definition, you can think of it from the general definition, of the expected value of discrete random variables, x plus y in this case. Okay, well, we have to think about this a little bit. So what does that mean? That's the same thing as the sum, as x runs from, well, maybe we individualize that. So we just look at f of x plus y of x given n. What does that mean? That's the probability that x is equal to little x and x plus y equals to little n, which is the same thing. Over, maybe I should write this on the slide. Wait just a second. What I was writing was correct, but this is the same thing as f sub x comma x plus y of xn over f of x plus y of n. That's the same thing as I was saying before. It's probability of x is equal to x and x plus y is equal to n over the probability that x plus y is equal to n. Okay. Now, here, this is the same thing as the top is. The probability that x is equal to x, and if we think about this second condition, with x, big X equal to little x. This is the same thing as y, since big X has to also equal little x. The y has to equal to n minus little x. Now, we have worked with independent Poisson random variables before with parameters lambda 1 and lambda 2. And if you look at their, if you look at the probability mass function of that, where these random variables are independent, we already said that that forms a Poisson random variable, x plus y would be. And so its probability mass function will be e to the minus lambda 1 plus lambda 2, lambda 1 plus lambda 2 raised to the n, all over, it should be all over n factorial. So I'll just write that down as 1 over n factorial. Now, this part right here we're going to be able to work with because x and y are independent, and so we can split this up as probability that x is equal to x times the probability of y is equal to n minus x. That's going to be my next line. So this is equal to, as I said, the probability that x is equal to x times the probability that y is equal to n minus x over this bottom. Now I'll write this over n factorial this time because I've got room. And now each one of these are Poisson random variables, so this is e to the minus lambda sub 1, lambda sub 1 to the x in this case, over x factorial. This is going to be e to the minus lambda sub 2, then it's going to be lambda sub 2 to the n minus x over n minus x factorial, and then all over this bottom. Okay, I've got enough room here to, you flip and multiply, so here's what you get. You get, I'll rewrite it this way. So I have n factorial will be in the top from here. Then I'm going to have over n minus x factorial, so I'm just going to look at that. Here I'm going to have e to the minus lambda 1. Here's another e to the minus lambda 2. And I'm just going to have that over e to the minus lambda 1 plus lambda 2 from the bottom here. Okay. Then I'm going to say this is lambda sub 1 to the x, lambda sub 2 to the n minus x. And then I'm going to rewrite this lambda sub 1 plus lambda sub 2 raised to n as lambda sub 1 plus lambda sub 2 to the x, lambda sub 1 plus lambda sub 2 to the, to the n, so this would be n minus x. I mean, if you multiply these two guys together, you add exponents, you just get n, which is what we have here. So that's right. But I write it in that way because it helps me notice a certain form here. Okay, so if you will, that is the first part with n choose x, that's what that would be. And then we would have lambda sub 1 over, I think it was lambda sub 1 plus lambda sub 2, all that's raised to x. And then it was lambda sub 2 over lambda sub 1 plus lambda sub 2 raised to the n minus x. And when I write it down in that form, okay, so what was that? That was f of x plus y, x given n. Okay? That's what this is. And if you notice, if you add these two together, you get 1. So this is 1 minus this guy. With that being said, this quantity right here is nothing more than the PMF. It's the PMF. Well, here's what I'll write. This is the PMF of a binomial random variable. So overall, what I can say is this. So the conditional PMF of x given x plus y, that's what we're looking at. I wrote it on the side there. Okay? For independent Poisson random variables is the PMF of a binomial random variable with P, what's P equal to? So P is equal to lambda sub 1 over lambda sub 1 plus 2, lambda sub 2, and the parameter n. That's what we have. Okay, so we can use that to answer the question that we posed. So, remember what we were asked. The expected value of x given x plus y equals n. That's the sum as x runs from 0 to infinity of x, f of x given y, oh well, it's x plus y, x given n, which is equal to the sum as x runs from 0 to n of x of x times here, this is, let's wait just a second. Well, it should be infinity, but that makes it only go up to n here for x, because x plus y, the biggest it can be is n. And so for bigger than n, when x is bigger than n, you would get 0 for this. X plus y can only go up to n. X times, here this was n, choose x, lambda to 1 over lambda sub 1 plus lambda sub 2, lambda sub 1. Raised to x over lambda sub 2, lambda sub 1 plus lambda sub 2 raised to n minus x. And here, you know, I made a mistake. I made a mistake on this other side of the board. And I said parameters, n. You know, that was right. That was right. Everything's good. Okay. So, this is correct. And having said that, this is nothing more than the expected value of a binomial random variable with parameters n and p equal to lambda sub 1 over lambda sub 1 plus lambda sub 2. So I know this is the expected value of that, which was n times p. So it's n times lambda sub 1 over lambda sub 1 plus lambda sub 2. That's what it is. And that's our answer. So that concludes this example. Okay, next we're going to look at a fact. So here's what it says. We let x and y be continuous random variables. With joint PDF F X comma Y. You can write down X comma Y here if you want the joint. Then the joint PDF of X and X plus Y is F of X comma X plus Y, and here this would be X comma T maybe, T. And that's equal to, so here's what's going to be, it's going to be F of X comma Y, so the joint between X and Y of X and T minus X. We're going to look at the proof of that, so that's the fact we're going to prove. Okay. Now this proof is going to be done by first assuming the hypothesis proved. We're going to let X and Y be continuous random variables. With joint PDF F sub X comma Y of X comma Y. Okay. Okay, so that's what we'll start off with. We're going to consider the joint CDF. So we're going to let the joint CDF cumulative distribution function of X and X plus Y be, so okay, here's what it is. It's denoted by big F, so X comma X plus Y, and I'm going to say that's little x T. Now, let's look at this. Note, what does this mean? This CDF with X and X plus Y of X and T, that's the probability that X is less than or equal to little x, and X plus Y is less than or equal to T. So if I draw this kind of region to see what we're talking about. Okay, so let's say this is little x right here. So for X to be less than little x, that's along to the left of this little x. Then let's say T is right here. It's a positive number. So here's T along the horizontal axis, not the vertical axis. And so this would be the X plus Y equal to T. And so if you want X plus Y to be less than T, that's everything below this line. And if you look to see what they have in common between everything to the left of the vertical line equal to X, it's this region here. So what I have then is that this CDF so if I describe this as a double integral, and let us use just the PDF, the joint PDF between X and Y. So this is the probability that these two things are happening. Maybe I need to write one last time. Yes, let me get this in. So right here, this is equal to, this part is equal to the probability X is less than or equal to X, and Y is less than or equal to T minus X. Okay? So it's that we can describe using the joint PDF between X and Y, not X and X plus Y, just that. So I'm going to describe this region. Maybe I have it right here. So F sub X, comma X plus Y of X given T equal to. So I'm going to describe that region in terms of that. It's a double integral. Okay. So I'm going to write down L, and here I'm going to write down, instead of, well, I'll write down X and Y. But instead of writing little x, little y, or little x, little t, I'm going to write just down UV. And here I'm thinking of this as U and this is V, even though this is Y and X. When I write down U, U is representing the horizontal axis. And we would integrate with respect to du dx. Okay, I know. Part here. So in the shaded region. But what would be our du dx? It'd be du dv. But I'm going to change that. I'm going to make it dv du. So v represents the y. And du represents the x. Now I look at the x values of this region, this horizontal part. It goes from minus infinity up to little x. So I put these dummy variables u and v here. Because our integral has to equal in terms of answers, in terms of x to t. So here, the x values run from, the horizontal values, the u values in terms of this function, run from minus infinity up to x. For each one of those, the vertical value, the y values, if you will, the v values, they will run from minus infinity up to this line. Okay, what is this line? Well, this line is 2 minus the first variable value. So this was an x, so t minus the first variable value is u. We're going to rewrite that on the side. That's what we do. So, again, just repeat it. So we see f of x and x plus y of x t. So here's what I have. It's nothing more than the integral from minus infinity to x, integral from minus infinity to t minus u, L, x given, x comma y, u v, d v d. That's what we have. Okay. So, now in previous facts, if you take the derivative, partial derivative with respect to x then t, t then x, is c df. Well, we've already proven as a fact that what that's equal to is the joint PDF between x and x plus y. So this is a little element. That's just by previous fact. Also, if I take these sequences of partial derivatives of this joint CDF, which equals to these derivatives this way of these double integrals, then what I can do is pull this integral, this derivative inside this first integral, because this first integral doesn't have to do with t. Partial derivative with respect to t of f of x of comma y, u v, f of d, dv, du, this. And then, I forgot an integral. There's integral from minus infinity to t minus u. So by the fundamental theorem of calculus, this first, or inner integral, that inner integral, by the fundamental theorem of calculus, is what we call Okay, so that's equal to the partial derivative, okay, with respect to x, integral from minus infinity to x. And by the fundamental theorem of calculus, we were doing with respect to b. So the L, the left, x comma y, we would have u, and instead of b, we would have stuck in t minus x. Okay? We'd have to differentiate with respect, it's t minus u, I guess. T minus u. We'd have to differentiate with respect to t, we would get nothing, times 1, I guess. And then it's d of u. Now, here, taking this derivative, using fundamental theorem of calculus, this ends up being little f of x comma y. Wherever there's a u, I'm going to put in x. So it's x t minus x. Then I have to differentiate with respect to x with just 1. So, combining those two things, what we have is L, the joint PDF between x and x plus y of xt is equal to the joint PDF between x and y, evaluate x and t minus x. And that's what we set out to prove. Well, there's another fact, an important fact I want to list, with proof. And so it says the following. It says, just let me write it down, as you know that x is a random variable. So the expected value of x is really equal to the expected value of the conditional expectation of x given y. That's kind of a nice, interesting fact. So remember, the conditional expectation of x given y is a random variable that's a function of y. So if you take the expected value of that, you get the expected value of x. Let's prove that. We'll prove it in cases. We'll partially prove it. I'll do one case. And leave the other case to you. Okay, the way we're going to prove that fact is we're really going to look at the right-hand side, the one where we're taking the expected value of the conditional expectation of x given y. So here's the proof. For case 1, we're going to have suppose x and y are both discrete random variables. Then, the expected value of the conditional expectation of x given y equal to y. Okay. So, this inner part is a function of y, and so this will be the sum over all y values of expected value of x given y equals y times the PMF of y. Let's substitute that equal to. So that's the sum over y values. Now the conditional expectation of x, that's the sum over x values of x times the conditional probability mass function of x given y. So that's that part. And here we have f sub y with y. Well, let's rewrite the conditional probability mass function in terms of its definition. Now, really, this has parentheses about it, okay? But this is a constant with respect to x, so I can pull it inside. Let me just do that for clarity in the next line. This is the sum over the y values, sum over the x's of x f sub x given y, x given y, f sub y of y. And let's replace this by what it's equal to. So this part right here is f of x comma y over f sub y of y. Here's f sub y of y. These two things cancel. So this is equal to the sum of the y, sum of the x's of x times f of x comma y. And I'm just going to stop there. Here, when you sum up x times the joint PDF between x and y over all x and y values, that's nothing more than the expected value of x. You can simplify that if you want by interchanging, simplify the long version by interchanging the sums, pulling out the x's, the sum of the y's of the joint is nothing more than the marginal of x, or the PMF of x. So you have the sum of the x's of x times the PMF of x, and that, of course, is expected value of x. But I'm just going to say, hey, we already know this is expected value of x. Oh, I said that's the end of the proof, but I should have got another case. But I'm not going to prove it. I'm just going to write a comment about it. So for case 2, x and y are both continuous. Here's what I'll tell you. This case is analogous. Case 1, where we use integrals. In case 2, instead of summations. And this might be something I ask you to do on homework. Or exam test, excuse me. Okay, we'll do one example and then we'll call it quits. So as an example, let's say Sam, it's a long worded example, is either going to read one chapter, I'm sorry, from his probability book, or one chapter from his history book. Okay. Suppose the number of misprints in a chapter of the probability book is a Poisson random variable with mean 5. Expected value is 5. Let's also suppose the number of misprints in a chapter of the history book is a Poisson random variable. Would mean two. Okay. Assuming Sam is equally likely to choose either book to read, either book, find the expected value of mistakes, misprints, if you will mind. Expected number of misprints Sam will encounter. Okay, before I leave this, I know you're writing things down. Before I leave this, look, we're wanting to find the number of misprints, the expected value of misprints. But really, that's going to depend on which book that he picks. And so there's going to be a conditional expectation, if you will, based on the number of misprints, the expected value of the number of misprints, given whichever book he picks. So that's why we can change the expected value of misprints into a conditional expected value, using the fact that we have. So here's the way I'll write it up. Let's let x equal to the number of misprints encountered. Let's let y equal to 0, let's say 1. Sam Hicks probability book. 0 if Sam Hicks history book. And so the expected value of x is what we're interested in. That's what we're interested in. But that's really the expected value of x given y. That's the same thing. Now, this is the, we usually write down y equal to y. This is the same thing as the sum over all the y values, so that's from 0 to 1, of the expected value of x given y equal to y, which is going to be easy to compute here, times f sub y of y. And so that's equal to the expected value of x given y equal to 0 times f sub y of 0 plus the expected value of x given y equal to 1 here f sub y of 1. Okay. So the expected value of mistakes that he'll run into if y is equal to 0. Y is equal to 0 is in history. And so if you know he picked the history book, the expected value of mistakes he'll make, well, let's give it to him. So that's 2. And what's the chance that he picks the history book? Well, they were equally likely the books were to be chosen, so that's 1/2. Plus the expected value, conditional expected value of x given y equal 1. Y equal 1 means he picked the probability book. So you know he picked the probability book. What's the number of misprints you expect him to run across? That was 5. And then what's the chance that he picked the probability book? That's 1/2. So we end up getting 7/2. And so that's the answer to our problem, 7/2. Okay, thank you very much. That's enough for today.